Good morning, everyone, and thank you for attending this webinar. It's both my pleasure and my honor to present our work to the Pell students and young professional community today. The talk today is titled Capacitor-less Photovoltaic Cell Level Power Balancing using Diffusion Charge Redistribution. I know it's probably a mouthful right now, but hopefully by the end of this talk, it'll make a lot more sense to everyone. This work was performed by myself and my colleague Ala Vestrus, with funding and support from Professor Stephen Lieb in the Laboratory of Electromagnetic and Electronic Systems at MIT. So I'd like to get started with a brief overview of the presentation. We will start with some background on why there's a need for maximum power point tracking for solar photovoltaic systems and how mismatch and asymmetry can negatively impact our ability to extract the maximum power from each PV element. We'll then discuss some of the previous approaches to address these problems and talk about the possibility of limitations of scaling these existing techniques down to the cell level. After that, we'll shift our attention to looking at some of the intrinsic properties of the solar cells, because their effects will become more and more significant as we scale maximum power point tracking down to the cell level. We will then introduce the new power balancing scheme, of course now with the parasitic elements taken into account, and discuss their trade-offs, illustrate the analysis, and conclude with experimental validation. Now I've also included a little preview of some of the work we've been doing and will be presenting in October at the International Conference on Renewable Energy Research and Applications. So hopefully you'll find that interesting as well. In general, I'll try to make this talk not only about how the approaches work, but also about our thought process and how we actually arrived at these solutions. So with that, let's get started on the background section, where we will discuss the need for maximum power point tracking and briefly cover some of the previous proposed approaches. So the first problem that's commonly encountered in a solar photovoltaic system is disproportionate energy loss. And this problem is mainly caused by asymmetries and mismatches in the system, which can result from things like shading, soiling, and aging. Here we're showing a shading example, and as you can observe in the table on the right, even if you were to shade only a small percentage of the overall panel area, you could lose a significant portion of the total power. For instance, the second row shows that even with a 6.5% of the area shaded, the overall power loss can be as high as 44%. Now, to understand the root cause of this problem, let's now take a look at how the solar cells are typically configured. Solar cells and solar modules are traditionally connected up in a series string, because stacking the cells and the panels together conveniently allows us to create a high enough voltage necessary to interface with a grid-tie inverter. So this configuration is also what creates what we call the weakest link problem. So let's shift our attention to the simplified single diode solar cell model on the right for a second. It consists of a photocurrent source in parallel with a diode, and together they create the IV characteristic shown on the top. To maximize the power extraction from the cell, it is very important to operate each solar cell at its maximum power point, where the IV product, or the area under the curve, is maximized. But with the series configuration, we're under the constraint of having the same current through each and every solar cell, which means that if there is mismatch, not all the cells can operate at their respective maximum power point, so we're losing power. Now, what's worse is when a cell is significantly shaded and actually becomes a current bottleneck in the system. And in the extreme case, if a photocurrent source completely disappears or goes to zero in one of the PV elements, there's no way to push current from the other PV elements through the diode in the reverse direction. So here is a simulated example with 5 cells. The x-axis is the output current, and the y-axis is the output power. If we were to shade one cell by 50%, this corresponds to a 10% overall shading, but in reality we are actually losing about 50% of the total power due to this weakest link problem. Now if we shade another cell by 75%, which is still less than 30% overall shading, we're going to lose about 75% of the total power. We can do a little better by incorporating bypass diodes, and this will provide a path for the current to flow around the underperforming cell. But this approach also forfeits any potential power generation from the underperforming cells. So in the example where one cell was shaded by 50%, instead of losing 50% like before, now we're losing about 20% because we're completely throwing away the power of one cell. In addition, bypassing results in a non-convex power characteristic curve, which complicates the MPPT algorithm. With multiple maxima, now it's much more difficult to find a global maximum. With bypass diodes, there is also additional loss incurred on the forward drop on the diode. So I've actually put a star next to diode loss because I know that TI recently came up with a product that's an active bypass solution to eliminate that additional loss. And finally, I'd like to point out that even though I've shown bypass diodes on every cell here, it's not typically done. Bypass diodes are usually applied to a group of solar cells within a panel. And this actually brings us to the next problem, which is hotspots. So we can rearrange the circuit on the right to see what actually happens when a cell becomes the bottleneck of the string. When the current is limited, the unshaded cells collectively can drop a high voltage across the shaded cell in the reverse direction. And this in turn can make the shaded cell go into reverse breakdown and start conducting current. However, even though the cell is conducting current, instead of generating power, the cell is actually dissipating power, and this creates a local hotspot. And a local hotspot is a serious problem because it creates, one, reliability concerns, two, accelerated panel degradation, and in the worst case, it can also constitute a fire risk. And because of the previous two problems, installation sites for solar PV must be very carefully screened and selected. And this results in a constrained feasible market size. So you can see on the house on the left, the solar installation is usually not recommended due to heavy shading problems because it's got trees on all three sides of the house. And on the house on the right, although a solar installation can be built, it has to be undersized to avoid shading and mismatch problem on the trees on the left. And in fact, in a survey conducted by NREL, the National Renewable Energy Laboratory in 2011, they reported that about 75% of the residential rooftop they surveyed were not suitable for on-site PV. So to address some of these problems, there has been a lot of research activities in the maximum power point tracking space. And there are essentially three approaches. So the first one is cascaded DC-DC converters, and the second one is microinverters, and the third one is actually recently proposed called differential power processing, which I will talk about on the following slide. The cascaded DC-DC approach basically places a converter at the output of each solar module or submodule, and this adds an extra degree of freedom to operate each solar module at its respective maximum power point. The converter can either be switched inductor or switched capacitor types. The microinverter approach essentially decouples each module from each other and optimizes the power output of each one individually directly onto the AC grid. But of course, being an inverter, there also has to be some form of energy buffering capacitors and current controlling inductors. And what separates these cascaded approaches from the differential power processing approach is the fact that they have to process the full power generated from the PV string, which is one of their major disadvantages. The differential power processing scheme solves the problem by only processing the mismatch power and not the common mode generated power. So if everything is balanced in the string, the differential power processing converters can simply sit out without having to process any power, resulting in no loss. There are two embodiments using inductors for current steering, illustrated here on the slide. And you can see again that some form of energy storage is required for this technique to work. So as discussed on the previous two slides, we can see that existing approaches all require some form of energy storage components to work. So their adoption has been limited to the module or submodule string levels. And it's indeed quite difficult to imagine requiring inductors or capacitors to be added on a per cell basis if we were to scale these approaches down to the cell level. But there is also significant benefits to be gained in scaling maximum power point tracking or power balancing down to the cell level. There is a statistical study published by IEEE showing that energy extraction improvement can be as high as 30% with maximum power point tracking on the cell level compared to that with module level maximum power point tracking. In addition, solving the problem at the module level also does not adequately address the hotspot problem either. So the question is really, can we scale maximum power point tracking down to the cell level? And more specifically, can we scale maximum power point tracking down to the cell level without requiring per cell energy storage components? And before we get to the answer, I'd like to show you the difference between module level and cell level maximum power point tracking in a couple of illustrations. So here we can see that there are essentially two levels of problems, the cell level problem and the module level problem. And with a module level maximum power point tracking solution, we're really only solving the module level problem. While these solutions can prevent the shaded panel from becoming a bottleneck and extract the available power from the unshaded panel as well as the shaded panel, the weakest link problem at the cell level is still there. As a result, a lot of power can be lost within the shaded panel where only a few cells are shaded. And again, the hotspot problem can still occur because it's not fully addressed by these solutions. With maximum power point tracking scaled to the cell level granularity, every cell, rather than panel, can operate at their respective maximum power. So it can recover all the power loss from the unshaded cells inside the shaded panel, and thereby significantly boost the overall power extraction. In addition, if we were to manage the cell voltage correctly, we can also eliminate the hotspot problem at the same time. So this is what our goal is. And this brings us to the next topic, which is solar cell parasitics. To reach our scaling goal down to the cell level, we need to investigate the solar cell's intrinsic properties to see if there's anything we can potentially leverage as energy storage. This is really something unique about performing power balancing at the cell level, because at the module level, most of the useful parasitic components will be diminished by the nature of the series combination. So let's begin with the full solar cell model shown in Dr. Catherine Kim's paper. In addition to the photocurrent source and the diode we've discussed before, there is also now a parasitic capacitance as well as a reverse diode to capture the reverse breakdown behavior. As you will recall, when the reverse bias of the cell exceeds the voltage VBD, the cell can actually begin conducting in the reverse direction while burning large amounts of power, resulting in a hotspot. So this model is very useful to characterize and examine PV behavior for hotspots. Now typically, when maximum power point tracking is considered, we're referring to a particular DC operating point. So the model is oftentimes simplified to what we've shown before, where the capacitance becomes an open circuit, and because we're under the assumption that we're extracting power from the PV element, reverse breakdown characteristics can also be removed. But for our purpose today, we're trying to figure out if we can leverage any parasitic component as a potential energy storage device for power processing. So we'll reintroduce a parasitic capacitance back into the model, and this is the model we'll be using moving forward. So here on the top left is a single diode solar cell model with the parasitic capacitance included. We're assuming the cell is operating in forward bias region, which is where we'll be operating when generating power. And typically in this region, the diffusion capacitance dominates and can be related to the diode voltage and current by the equation shown on the slide. As you can see, it's an exponential relationship with voltage and a linear relationship with current. Now, to verify this relationship in the context of a switching converter, which is how we'll be exploiting the parasitic capacitance in our circuit, we had constructed a circuit with two switches, an external capacitance, an external capacitor of known capacitance. In phase one of the switching cycle, the external capacitor is connected in parallel to the solar cell. And in phase two, the external capacitor is disconnected and discharged through the second switch. What that means is that during phase one, the photocurrent charges the parallel combination of the diffusion capacitance and the external capacitance. And during phase two, the photocurrent charges the diffusion capacitance alone. And from the ratio of these two charging slopes, we can then extract the value of the diffusion capacitance. And it actually behaves exactly as the model predicts, linearly, with a diode current. And on the top right, we have an example transient waveform of our measurement with the slopes and different phases labeled. And on the bottom right, we have the derived capacitance value versus the current plotted to show that it's actually a linear relationship. So having verified the capacitance relationship in the context of a switching converter, the next step is to make sure that this intrinsic capacitance can actually be used as a power handling device for power balancing. And to do so, we had designed a circuit with 3 solar cells and a single capacitor. The 3 solar cells are connected in a series string, while the flying capacitor takes turn in connecting to each solar cell sequentially. Since there is no locally added energy storage capacitor on the solar cells, they must rely on their own internal diffusion capacitance for energy buffering if needed. Consequently, we're calling this the Single-Capacitor Diffusion Charge Redistribution, or DCR for short. It can be seen that under match condition, the maximum power can be extracted by drawing IMP from a string, and the flying capacitor will process 0 power as the cells would exhibit identical voltages. So differential power processing is achieved. Things get a little more interesting when there is mismatch. Suppose we have partial shading on the bottom cell, and the shaded cell's maximum power current is reduced to 40% of the original. In order to extract all the power from the string, we must extract the maximum power point current from each and every cell. With this configuration, let's assume we demand the average cell current at the output, which is now 2.4 divided by 3, or 0.8 times IMP. Under this assumption, during phase 1, an equivalent of 0.2 units of charge will be transferred to the flying capacitor. During phase 2, another equivalent of 0.2 units of charge will be transferred to the capacitor. And finally, in phase 3, the total 0.4 units of charge will now be transferred to the bottom solar cell, so the flying capacitor achieves charge balance. If the diffusion capacitance can indeed store this energy, then we should be able to draw 0.8 IMP out of the entire string without being limited by the bottom cell's current generation capability. And when this charge balance happens, it will be as if the solar cells are all being placed in parallel. So we actually put this to a real test in an experiment. So we built a small prototype for validation, and the plot on the right has the output current on the x-axis and the output power on the y-axis. As shown, the single capacitor diffusion charge redistribution scheme in green can extract much higher power under partial shading condition when compared to the series string in red and the series string with bypass diodes in blue. So we have verified and demonstrated that the diffusion capacitance can actually behave as a power handling device for power balancing. And again, this configuration achieves differential power processing, and as you can see, a convex output power characteristic. However, remember that a flying capacitor is still required in this configuration. So this is really just a setup to verify the utility of the diffusion capacitance. Moving forward, we'll still need to come up with a different configuration to remove all the energy storage requirements. So if we think about what's on the solar panel, the most abundant resource that's everywhere is actually the solar cells themselves. So the question is, can we replace the single flying capacitor by a solar cell, which can be treated as essentially a capacitor in parallel with the current generation source? Furthermore, can we come up with a scalable topology to apply this to a structure that is much bigger than the 3 cells we were showing before? So it turns out we can, and this is a fully capacitorless diffusion charge redistribution circuit with a fairly simple and fully scalable ladder structure. Now the explicit trade-off we're making for eliminating all the external energy storage is to settle for processing part, or about half, of the common mode generated power. But this approach also has many, many advantages, which in our opinion outweigh all the trade-offs we have to make. First, the cells are placed in the ladder string, so we can still stack cells up together to create a high string voltage that can be used to interface with existing inverters. And by switching the cells, we can make them appear in pseudo-parallel, so that power balancing occurs naturally as if the entire string is behaving like a single supercell. Being in pseudo-parallel also enforces similar voltages on all the cells, and this eliminates the possibility of reverse biasing and hotspot formation completely. And since we have achieved cell-level power balancing without using any external energy storage components, this represents achieving the finest maximum power point tracking granularity at the minimum cost of power electronics. Since we're actually making an explicit trade-off to process part of the generated power, let's go ahead and analyze how much the insertion loss actually is from this distributed switch capacitor type converter. We'll define insertion loss as the loss compared to a series string with no power processing on the uniform radiance condition. The conversion efficiency of a single input, single output switch capacitor circuit has been well studied using Telegreen's theorem, and from Dr. Siemens' formulation, the efficiency can be written in terms of an effective output impedance and a load impedance as illustrated in the switch capacitor converter model shown on the slide. The output impedance has 2 asymptotic limits, the slow switching limit and the fast switching limit. In the slow switching limit, the capacitors are given sufficient time to charge and discharge, so the capacitive charging and discharging loss dominates, and the output impedance is proportional to 1 over CF, where F is the switching frequency. On the other hand, in the fast switching limit, the capacitor voltages actually change very little, and they essentially behave like voltage sources. So the loss is dominated by conduction losses through the switches, so the output impedance is proportional to the RDS(on) of the switches. So let's take a look at how we can generalize the single input, single output switch capacitor analysis to this case with distributed power generation. we'll use a 3-2 configuration as an example to perform this analysis, where 3 is the number of cells in the load connected string, and 2 is the number of cells in the ladder connected string. We'll model each solar cell as a current generation source in parallel with a capacitor. And this is a reasonable model because switched capacitor converters are inherently current transformers. There are 2 phases of operation. In phase 1, the up switches are active, and in phase 2, the down switches are active. Charge flows are labeled for each component, where the subscript denotes the component type and its index, and the superscript denotes the different phase of operation. So for example, QC1 of 1 denotes charge flow out of the diffusion capacitor of the first solar cell in phase 1, and QPH2 of 2 denotes the charge flow out of the second solar cell in phase 2. Now to solve for the insertion loss, we first begin with the assumption of uniform irradiance and the fact that the photocurrent sources are constant current sources. So they generate equal amounts of charge, QPH1 and QPH2, in the 2 phases respectively. Next, we can use capacitor charge balance, which states that the net charge flowing into a capacitor over a complete switching period in steady state operation must be 0, so that the capacitor voltages do not run away. And with capacitor charge balance, we can see that the sum of the total charge flowing out of a solar cell over the 2 phases must add up to QPH. Finally, we assume that we have some form of maximum power point tracking capability at the inverter level, and the inverter demands a constant output current. So Qout1 is equal to Qout2, and it's sum to Qout. And with the use of KCL, we can write down additional sets of equations to relate the charge flow quantities. Specifically in phase 1, we have QPV1 of 1 plus QPV2 of 1 is equal to QPV3 plus QPV4 is equal to QPV5. And a similar relationship can be written down for phase 2 as well. So here's a quick summary of all the equations we have just discussed. With these equations, we now have all the information we need to solve for the charge flows into and out of the capacitors for deriving the SSL insertion loss, as well as the charge flows across the switches for deriving the FSL, fast switching limit insertion loss. The point of the 3-2 configuration exercise is to illustrate the process of solving such a problem. So instead of showing the result for the 3-2 case, I'd like to show a more generalized results next, which is for an arbitrary sized DCR string with n cells in the load connected string and n-1 cells in the ladder connected string. So we have 2 n-1 cells total. The insertion loss in the general case actually reveals a lot of interesting properties. So as you can see, the slow switching limit insertion loss is proportional to 1 over Fc, which we expect. But what's interesting is that it's proportional to the ratio of the maximum power point current over the diffusion capacitance. Now the current generating capability per area and the diffusion capacitance per area are both material dependent quantities. Hence, given a solar cell material, the ratio of IMP to CD is actually fixed, so the loss cannot be optimized based on changing the cell size. We also note that the SSL insertion loss is approximately constant for large N, so it will always persist in the system unless switching frequency can be arbitrarily high. On the other hand, the FSL, the fast switching limit insertion loss, is proportional to RDS-on as we expected, but it's actually inversely proportional to the number of cells N. Now this can be understood intuitively by noticing that the conduction loss is approximately fixed at I squared R, but the total generated power from the ladder string increases linearly with N. So with that, the percentage insertion loss actually decreases inversely proportional to N as well. So this is why we can increased number of cells to make the fast switching loss insignificant. And to give some perspective with actual numbers, let's do an example calculation. So let's assume N of 20, so we have about 40 cells total. The maximum power point voltage of 0.5 volts and a maximum power point current of 2 amps. The diffusion capacitance for the monocrystalline solar cell we had characterized in this case would give about 9 microfarads. And if we were to switch our switches at 1 megahertz with an RDS on of 15 milliohm, we would have a SSL insertion loss of about 3.5% and an FSL insertion loss of about 0.6%. And combining these two loss mechanisms using the root of their quadratic sums, the total insertion loss can be calculated to be about 3.54%, which is very manageable and relatively small for a system with absolutely no external energy storage. So finally, we have an experimental setup to validate the derived theory. Our experimental setup is a 3-2 capacitorless DCR setup with 5 solar cells total. In fact, to ensure fair comparison across different configurations, the prototype was designed to be reconfigurable between a series string with bypass, and the proposed DCR arrangement, so that all measurements will be performed using the same set of solar cells under the same irradiance condition. The IV characteristics and the output power characteristics are measured using a DC electronic load operating in constant current mode at the output. The DC electronic load is programmed to sweep the output current at about 2 amps per second, and the experimental PCB picture is shown on the top right, and an example measured waveform versus time is shown on the bottom right. Here are some measured power characteristics under different shading conditions. The x-axis is again the output current, and the y-axis is the output power. On the left, we have a case where 2 out of 5 cells are shaded by 40%. And on the right, we have 1 cell shaded by 40% and another cell shaded by 75%. Under both conditions, the latter DCR string is able to successfully extract significantly more power compared to the series string and the series string with bypass diodes. And what's interesting is that the output power characteristic is also convex, which verifies the behavior as a single supercell. And again, we did not, this configuration did not add any external energy storage. And this table summarizes some of the tests we performed, and I want to quickly highlight a few key numbers. First, the conversion efficiency was measured to be 94.7%, and this is actually higher than the calculated insertion loss of 7.1% with n equals 3. Now this can be attributed to a variety of factors. The first one is additional recovered losses from the cell mismatch. And the second one is actually we had some non-uniformity in our lighting source. So all that mismatch and asymmetry is naturally recovered using DCR configuration. And also, these insertion loss numbers may sound a little high compared to the 3.5% we calculated before, but keep in mind that this is because n is still very small. With n equal to 3, the FSL insertion loss component is still significant. So that contributes a lot to the total insertion loss. Next, with the two shading conditions, we have 16% and 23% overall shading respectively under the two conditions. And if we look at the extracted percentage, they're shown to track this 1 minus the shaded percentage very closely. So we have 83.3% and 77.1% respectively. And essentially this implies that what you shade is what you lose, which means that the string is effectively behaving like a single big solar cell, or what we call the supercell. So to quickly wrap up what we've discussed so far, we have introduced a new power balancing scheme called diffusion charge redistribution to perform power optimization at the cell level by transforming the string of cells into an effective supercell. And this represents the finest power optimization granularity at the minimum cost of power electronics because we're not using any additional and external energy storage components. We've also shown that this approach results in small and manageable insertion loss. With cell-level power balancing, the average energy extraction improvement can be expected to increase by up to 30% compared to 16% with the current state of the art solutions, and the hotspot problems can be avoided as well. We have also demonstrated a proof of concept system that have shown to extract significantly more power on the various partial shading conditions. So the question now is what's next, and can we make further improvements to the proposed diffusion charge redistribution scheme? And is it actually possible to propose a new structure that eliminates insertion loss? Now keep in mind that any modification we make now must follow our original constraint of not requiring per PV element energy storage components. So we don't want, we've worked really hard to get rid of them. Let's not bring them back. So let's quickly remind ourselves where the insertion loss is actually coming from. Basically, all the power generated from the ladder connected string has to be processed through the switching structure. So we're always processing approximately half of the common mode generated power, which is undesirable. Now, what if we were to eliminate the ladder connected string altogether? And we can do that by now optimizing the circuit at the string level and extracting power directly from the ladder connected string as well. So we would have a structure that looks something like this. So this can either be done by splitting the inverter into two, or using a current, or inserting a current splitting block in front of an existing inverter. And we'll actually cover this in more detail at the conference next month. The advantage of such approach is, one, we achieve differential power processing. And at the same time, we still don't require any per cell energy storage components. We can also potentially improve system robustness with inverter redundancy. And perhaps most importantly, now that we're not limited by the common mode conversion efficiency, we have the flexibility to lower the overall DCR switching frequency. So I'd like to show you two simulations before I wrap up. Here we have, again, x-axis being the output current and y-axis being the output power. On the plot on the left, we're comparing a 9-series string to a 5-4 DCR string to a 5-4, what we're calling differential DCR string with a split current source inverter. In this case, there is uniform irradiance, so the current split ratio is expected to be even at 0.5. And we can see that insertion loss has indeed gone to 0 with this configuration compared to the original DCR. On the plot on the right, we're showing a simulation with 4 cells partially shaded. And under this condition, the additional degree of freedom in the current splitting ratio can actually be used to minimize the amount of power processed in order to maximize the power extraction. And the full paper and the presentation in October will also show power contours versus both output current and the current splitting ratio and discuss how to perform that power optimization. So this will conclude the webinar presentations today. I hope you have found this talk interesting and useful. If you have any questions that we won't get to answer today in the Q&A session, please also feel free to send me an email at arthurhc@mit.edu, and I'd be happy to take questions now.